Hi, this is Will, and this presentation will go over the Convair XFY-1 Pogo. In 1950, the U.S. Navy issued a competition to aerospace companies to develop a convoy fighter. And the concept of a convoy fighter is a vertical takeoff and landing interceptor that could be mounted on naval vessels, and upon detection of a radar threat could be launched and engage an enemy aircraft and either destroy it or hold it at bay long enough for carrier-based fighters to come in and protect it. This was met with proposals by Convair, Lockheed Martin, and Goodyear. So here, this is the Convair proposal, which is what we're talking about. This is the Lockheed proposal. This is the Martin proposal, and this is the Goodyear proposal. Only the Convair and Lockheed proposals were accepted to continue to a prototype stage. So that's what you see here. The Martin Goodyear models only made it to the conceptual design stage. So the basic design criteria of this aircraft could be summarized as such. It needed to be extremely lightweight. It needed to have adequate stability and control at all angles up to 90 degrees. And it also needed to be compact and very strong so that you could fit it on virtually any ship. It is kind of shown here in these conceptual drawings for what operation might have looked like. It also needed to have low drag at transonic speeds. So some key design features to keep in mind. We have the power plant. The aircraft was powered by the Allison YT-40A14, which is really a mating of two Allison T-38 turboprop engines to a single gearbox that then provided power out to the contra-rotating propellers via concentric shafts. The production variant would have used a higher power version called the XT-40. Another thing to note is the delta wing configuration. So it has a very high sweep, and it was employed because of its good high alpha characteristics and also very compact planform. So at high angles of attack with power, this aircraft would have very favorable stall characteristics and still be able to maintain control. So here, for comparison purposes, this is figure 1.17 from the book, and we're showing the location of that YT-40 power plant along with other historical data. So it provides some context as to how powerful this engine was. So continuing with design features, the actual propeller employed was a 16-foot diameter contra-rotating six-bladed propeller, and its 6 is in 3+3, as can be seen in the wind tunnel test model here. The production variant was to have an 8-bladed 4+4 propeller, but these were not in mass production at the time, and so they used the 3-bladed propellers. The aircraft also had the ability to rotate the pilot's seat during takeoff and landing through 45 degrees. So this was to try and aid the pilot in viewing the ground by looking over his shoulder during takeoff and landing. Prior to any actual flight testing, there was extensive flight testing of subscale models, and you can see this throughout here. Right here, these were all conducted at NASA Langley, and this is their control line test flight rig. So they have a safety power cable connected to it to catch it when it falls. This is plotting the position of the aircraft center of gravity over time with various flight trajectories for takeoff into a headwind. And this type of testing was conducted in an open wind tunnel and utilized operation like this, where once again they had the safety tether and they had a pitch pilot, power control, and yaw and roll pilots all separate. And these were all filmed for analysis later. And then finally up here, this is the aircraft in the NASA Langley spin tunnel to observe the flat spin characteristics. So for actual flight testing, before even free flight testing, tethered flight testing had to occur, and this was conducted in the Moffett Field blimp hangar. The aircraft had the top of the propeller hub removed, and a safety cable was attached to that, as well as along the onto each of the wing tips and the vertical stabilizers. And the pilot was able to take off and basically do a tethered hop to analyze flight control in a hovering condition. This is figure 2.6 from our textbook for reference, and it shows where the Pogo lies in terms of hovering efficiency and disk loading. So some final notes on this airplane. It was really fast. It had a maximum flight speed that was projected to be over 530 knots. In testing, it didn't achieve this full top speed, but the speed was remarked upon. With throttle at idle, level flight speed was in excess of 300 miles per hour. Also, landing it was extremely difficult. There was only one test pilot present with this through the duration of the testing campaign, and he was only able to control this and perform landings after hundreds of hours with tethered flight of this aircraft, because it doesn't behave quite like an airplane. It doesn't behave quite like a helicopter in that mode of flight. It maintains control through the aerodynamic control services, but throttle is what's effectively providing your altitude control. So due to that reason, and then also the fact that by the time this was coming to fruition 5 years later, fighter aircraft were now able to go in excess of Mach 2, and the use of a propeller aircraft was looking less and less like a good idea to the Navy. So the project was canceled in early 1955, but it remains a really cool relic of the era. And then just as a side note, this is a still from a testing campaign where they were testing the ejection seat from this aircraft. And luckily for the pilot, this is a dummy pilot. They discovered that unless the aircraft was in excess of 200 feet of altitude, ejection could not occur safely. So this guy would be doomed. Anyway, that's all. I hope that this was enjoyable and informative. Thanks.